Hello, welcome to the quick video on magnetism and electromagnetism, which is the final topic for physics paper 2. Okay, this is going to be fairly quick, hopefully. It's not a huge topic. So the first thing we need to remember is all about basic bar magnets. They're also known as permanent magnets because they are always magnetic. They don't lose their magnetism. The first thing you need to know is that they have poles. They have what we call a north and a south pole. Every magnet has got one of each. Okay, sometimes it might be called a north-seeking pole because if you hung it on a piece of string and let the bar magnet spin round, it would point towards the north, and that will be the north end or the north pole of the magnet that will be pointing northwards or seeking north. So it's called a north or north-seeking pole. You need to know that opposite poles will attract. So if you put a north and a south pole of a magnet, often coloured one blue, one red, there will be a force that attracts them and pulls them together until they touch. If you put two like poles together, for example, on my diagram I put two norths, then they will repel each other and there will be a force pushing them away from each other. You need to be able to draw the magnetic field lines around a bar magnet, they look like this. Fairly terrible drawing, as usual for me. Okay. You can't see a magnetic field with your own eyes, but it's there all the same. So to draw one of these, you draw the bar magnet. Doesn't matter which end is north or south, but please draw north and south on there. And then all you do is you draw, I always think it looks like sort of a bit like an apple core maybe, or something like that, or maybe an onion. Just do 2 or 3 lines. I suppose I could add one more there like that. Okay, so you just do that, and they build up on top of each other. And then at the ends, they kind of come out like that. The important thing is, when you draw them, you must always put the little arrow on there, because it might be 2 marks to do this. 1 mark will be the shape, and the second mark will be the arrow. And the important thing about the arrow is that the arrow always points towards the south or away from the north. Okay, so you can see on here, we've got them pointing away from the north towards the south. But even at the north end, where there is no south, the arrows point away from the north. Okay, so everything points south on the field lines, and you need to put that on there. Okay. Right then, just going back to bar magnets attracting and repelling, you need to be able to draw the field lines to show that. So where we've got a north and a south, and they're attracted, you get a nice straight line down the centre, pulling that one towards that one, and then you get more lines like that on either side, and they start to curve on either side. Okay, always try and draw 5 lines. Okay, 5 lines, and again, you notice all the arrows point to the south. When they're repelling, I always think it looks like sort of a pair of curtains that are kind of pulled back. If you look at that, it looks like a pair of curtains that have been pulled back because it's daytime. So if you're not sure how to draw it like that. Make sure these lines don't touch each other. And again, don't forget that the arrows need to point towards the south. Okay, if these were both north, you'd have the arrows pointing away from the north. Okay, and then you draw another pair of similar curtains down there like that. Okay, so you end up with that shape. All right. It's worth saying that the strength of the magnetic field is shown by how close the lines are together. The closer the lines are drawn, then the stronger the magnetic field is. However, there is another word we use for magnetic field strength, and it's slightly confusing because it's rather old-fashioned sounding. You will not see magnetic field strength written in an exam. You will see it called magnetic flux density. Okay, now that's a bit confusing because it doesn't really mean a lot to most people. But when you see that, just remember it just means the strength of the magnetic field. So the higher the magnetic flux density means the higher the magnetic field strength. So a strong magnet has got a high flux density and a weaker magnet has got a lower magnetic flux density. So don't be put off if you see that in a question. It just means that. Okay, and as I said, the closer the lines are together, the higher the flux density. Right then, how can we actually have a look at magnetic fields? Well, the way that they say you need to know is using those tiny little compasses that we call plotting compasses. So you can see I've drawn a bar magnet here, and we've got our north and south. Excuse me. And you notice that, so what I've done is I've put plotting compasses in about 5 different locations there, possibly 6, actually no, I count it, 6 different locations. And you can see that the arrow will point away from the north. So the arrow will point away, so each little location you put it, and then you could join that together, and that would give you the field line. okay, and the arrows would point south. So using the little plotting compasses, you can see the shape of the field line. Of course, another way to do it is to put the magnet underneath a piece of paper and sprinkle iron filings on it, and you may remember seeing your teacher do that, and you get a lovely magnetic field pattern. Okay, right, so bar magnets are permanent magnets. They are always magnetic. However, there are also another class of magnet called induced magnets. Induced means you make something into something. So these are things that are not normally magnetic, or not normally magnets, but they can become magnets if you put them in a magnetic field. And the most obvious example, if you put a paper clip on the end of a magnet like that, of course it's attracted to and held on to the magnet, but now that magnetic field has turned that paper clip at the top into another little tiny magnet. And we call that an induced magnet, and that will allow another paper clip to stick to that, and usually you can get a few hanging off each other. So these are the induced magnets, because if you take them away from the actual permanent magnet, they lose their magnetic ability very quickly, and they don't normally act as magnets. Okay, another way to induce a magnet is using electricity, and so here we go. So current, electric current and magnetism. So a conductor, we mean a wire or a metal rod or something like that, carrying a current through it has got a magnetic field round it. You can't see it, but it's there. This is our wire here, our nice straight wire between these two dots, and you can see it's been connected to a voltage source, a battery there. And you can see I've drawn the magnetic field. So around a straight wire, you get a circular field. It looks rather like a target or a dartboard, I always think. So that's the shape of it. It's circular, and the centre is right on the wire. If you have to draw one of these, don't worry about north and south if you're not given north and south. Just make sure you put some arrows all pointing the same way. And that way you show that at least you know that the field has to have a direction to it. I've just made a little point here. Don't forget, real electricity actually flows from negative to positive. But when it comes to electromagnets, we've got this weird old-fashioned rule called conventional current, that electricity flows or current flows from positive through to negative. Okay, that's not what really happens, but if electromagnets only, we use that rule because historically the people that worked out all the rules to do with electromagnets didn't know which way current flowed, so they decided it flowed from positive to negative, and all the rules follow that. Okay. I've put a note here saying right-hand rule. That should actually say right-hand grip rule. And all that is a way, if you've got a situation like this where you've got a conductor, so let's use my pen as a conducting wire, okay? So we're going to assume that the positive end is where my hand is over here, and the negative end is over here, so the current is flowing in that direction. The right-hand grip rule allows you to show which way the magnetic field arrows should be drawn on something like this. So you just literally grip it in your right hand with your thumb pointing in the direction that the current is flowing from positive to negative, and your fingertips show where the arrows should go. So if these were magnetic field lines, I would draw arrows pointing towards my fingertips. Okay, right then, we're getting there. So moving on with magnets that are magnets because of an electric current. If we move on from just a straight wire, which we talked about a minute ago, we have a thing called a solenoid. And a solenoid is just a coil of wire that's been wrapped round, as you can see in my diagram there, and then connected to a battery or another voltage source. What you need to know about that is that when it's switched on, you get a magnetic field that is this shape. And I always say to my students, it looks like a butterfly. So if you kind of draw butterfly wings or something like that coming out, or maybe like an onion when you cut it in half, not sure. But the point is, it looks like that. Okay? You don't need to know or worry about which way the current's flowing and which ends up north and south. But what's important is if south is shown on a diagram and you have to fill in the field, that you have the arrows pointing towards it. If you are asked how to swap the direction of that field, all you would have to do is to swap the direction of the battery, or swap the direction of the current. So you just turn the battery round and send the current the other direction, and this will become south and that will become north. Okay, so the other thing you need to know about these is if you wanted to increase the magnetic flux density, don't forget that's just the magnetic field strength, you've got three options. You could cram more coils in the same length, so you could like squash the coils closer together and get more of them in the same length. You could increase the current through the coils, or you could put a soft iron core, so it's just a core of iron, made of iron, down through the middle of the coils. And if you do that, that makes the final thing on this video, which is an electromagnet. An electromagnet is just a solenoid with an iron core. And what the iron core does is it concentrates the magnetic field. So that means the magnetic flux density, magnetic field strength, is higher. So it makes it a stronger magnet and more useful. As you can see from my terrible diagram, we've got our solenoid with a soft iron core in it. The field looks just the same as the solenoid. So if you had to draw that, it would look just the same as the solenoid, which is the one up here. The only difference would be the lines would be closer together because it's got stronger magnetic field, a higher magnetic flux density. So the lines would be closer together. And again, to increase the magnetic flux density or increase the strength of that electromagnet, you would cram more coils in along the same length, or you would increase the current flowing through it. Okay, there you go.